Okay, guys, so we need to finish up our notes on properties of matter, and we're going to do the law of conservation of matter. So we are on page 30. Remember, I had you write those numbers in the lower right-hand corner. So in your book down here, you should be adding in page 30. So we started with, what is matter? So I'm going to have a little video here for you to remind yourself what matter is.
Everything you've ever seen, everything you've ever touched is made of matter. Check it out. Matter is what everything is made of, from the grass on earth to the stars above. Matter is everything that you touch, your notebook, your baseball, even fruit punch. Some matter you can hold in your hand. Can you breathe matter?
Yes, you can!
Matter can exist in 3 different states. That's solid, liquid, and gas, okay. A pillow is a solid, so is a door. The walls, the table, the ceiling, the floor. The atoms are packed tight like the halls at dismissal. Moving around quickly is a real issue. Now a liquid could be oil, water, or paint. You could catch it in the cup outside when it rains. The atoms of a liquid are a bit more loose. Liquid takes the shape of the container you choose. Now gas, a state of matter that's hard to see. It fills up balloons, it's the air that you breathe. It's atoms, are loose like kids at recess, moving all over the place, they don't rest.
What's matter? Anything that takes up space, made of little tiny atoms to give it shape. When it gets hot or cold, atoms rearrange from solid to liquid to gas, okay?
What's matter? Anything that takes up space, made of little tiny atoms to give it shape. When it gets hot or cold, atoms rearrange from
solid to liquid
to gas, okay?
Here's a fact that might seem strange. Did you know that matter's state can change? Heat gives energy to atoms, so heat makes them speed up, cold makes them slow. Think of a liquid, water in a pot. Turn up the heat, the water gets hot till it boils and evaporates. The water's now a gas, its state has changed. Now put that glass of water in the freezer, it turns into ice. Guess the reason? Low temperature slows the atoms down. The water's now a solid, atoms don't move around. Now it's ice, but it can change back into a liquid, and that's a fact. Put the ice on the table, watch it melt quickly. The states change again, from solid to liquid. Temperature changes, the energy matter has. Solid, liquid, gas, known as the states of matter. Don't get mad at it, we pull matter out of the hat like a rabbit. What's matter? Anything that takes up space, made of little tiny atoms to give it shape. When it gets hot or cold, atoms rearrange from solid to liquid to gas, okay?
What's matter? Anything that takes up space, made of little tiny atoms to give it shape. When it gets hot or cold, atoms rearrange from
solid to liquid
to gas, okay?
So that was fun, and I hope that you now have a better idea of what mass and matter are. And now we're going to learn about the law of conservation of mass. So the law of conservation of mass is a principle that states the total mass of the reactants equals the total mass of the products in a chemical reaction. And now you're going to take a look at what a chemical reaction is and what the actual law of conservation of mass is.
Yo, in a chemical reaction, substances called reactants interact to produce one or more new substances called products. There are 4 characteristics that are true of any chemical reaction. You want to know what they are? Pay attention, because here we go. 1. A chemical reaction's always the same. Do the same reaction again, it won't change. Reactions occur in predictable ways. It's not random like pigs flying all over the place. The same reactants produce the same products, and it doesn't matter when or where, honest. Like if we burn sugar, then every time the products will be water and carbon dioxide. Number 2, all matter is conserved. Atoms aren't created, they're just rearranged. Observe these 2 substances, called A and B. They might react to produce a new compound, C. It's now AB. That's a synthesis. When substances come together, get the gist? In decomposition, molecules break apart. That's not easy to mend, like a broken heart. If it's displacement, synthesis, or decomposition, no new atoms are created. Listen, what happens in a chemical reaction? What happens in a chemical reaction? Substances react in predictable ways. Matter is conserved, not destroyed or made. Products have different properties than reactants. Energy is released or stored back in. Substances react in predictable ways. Matter is conserved, not destroyed or made. Products have different properties than reactants. Energy is released or stored back in. Moving on, number 3, the products have different properties than the reactants. Got it? If we look at the properties before and after, we can tell if a reaction has occurred. Moving back to the sugar that we burned. Word, when that happened, the odor changed up because of the chemical reaction. The product smells different than the reactants did. Plus, not to mention, the color and the taste have switched up. Now, number 4, this is what we will discuss. In a chemical reaction, energy can either be stored or released and let free. When it's released, we call it exothermic. And when it's stored, that's endothermic. The energy can be in many different forms, which include light, heat, or chemical energy. Now let's return to take another look at the sugar that we burn. The energy and the chemical bonds break, they escape in. That's an exothermic situation. What happens in a chemical reaction? What happens in a chemical reaction? Substances react in predictable ways. Matter is conserved, not destroyed or made. Products have different properties than reactants. Energy is released or stored back in. Substances react in predictable ways. Matter is conserved, not destroyed or made. Products have different properties than reactants. Energy is released or stored back in. What happens in a chemical reaction? What happens in a chemical reaction?
Still trying to turn lead into gold? Hey, isn't this just food coloring? Dear Tim and Moby, what is the law of conservation of mass? And what happens if you break it? I love you, Marianne. Thanks. You can't actually break the law of conservation of mass. It's not that kind of law. In science, a law is a generalization about how the physical universe works. The law of conservation of mass basically means that substances can't be created or destroyed. Or, in the language of chemistry, the mass of the reactants in a chemical reaction always equals the mass of the products. Yeah, let's take a look at some of those terms. First of all, mass is the amount of matter a substance has. Unlike weight, which changes depending on how much gravity is present, mass stays the same no matter where you are. So, although you may have different weights on, say, the Earth and the Moon, your mass always stays the same. We're good? Okay, next. A chemical reaction is when two or more molecules interact to form different molecules. For example, hydrogen and oxygen react to form dihydrogen monoxide, or water. In that reaction, hydrogen and oxygen are the reactants, the substance that are around at the beginning of a chemical reaction. And the water is the product, or what's around after a chemical reaction takes place. The law of conservation of mass states that the mass of the reactants must equal the mass of the products. Well, I know it seems kind of obvious. Stuff can't just disappear or appear out of thin air. And before the law was actually written down, people had been proposing the idea for centuries. Probably the first person to propose the law in a scientific way was Mikhail Lomonosov in Russia in about 1748. But his work wasn't known outside of Russia until much later. In the 1780s, a French guy named Antoine Lavoisier came up with a more precise description of how the law works, so we usually think of him as its discoverer. Yeah, sure it's useful. If you only know part of the mass of the chemicals in a reaction, you can use the law of conservation of mass to figure out the rest. Let's say you have 4 grams of hydrogen and 32 grams of oxygen. By adding the masses of the reactants together, you can figure out the mass of the product, 36 grams of water. You can do it backwards too. Potassium oxide combines with water to form potassium hydroxide. So let's say you have 18 grams of water. How much potassium oxide do you need to get 112 grams of potassium hydroxide? Yep, you need 94 grams of potassium oxide. Yeah, you didn't use enough. It takes 250 grams of blue food coloring to turn lead into gold. Yeah, I'm joking.
So we do have a lab today, so make sure that you are filling this out with me because I'll be checking it before you can move on to lab. So what does the law of conservation of mass mean? If you were paying attention to those videos, a law is a generalization of how something works. And it cannot be broken. Just like a rule or a law of driving, you don't want to break it. Obviously, we as humans can break laws, but we shouldn't. But laws in science cannot be broken at all. Conservation means saving something, keeping it constant or the same. So to conserve something, to conserve water, to conserve your energy is saving it, keeping it the same or unchanging. And then mass has to do with matter, and mass is the amount of matter or stuff that something has. So we have mass, and that's actually what they take at the doctor's office. Even though we call it weight, it is our mass. It's the amount of stuff that we have. All right, so then we're going to do the first part of the lab together. So there's an example on the next page, page 31. And so it's called the Law of Conservation of Mass Activities. We'll do the first one, like I said, together, and then you'll have time to work in partners or groups of 4 to do your own investigation. So on page 31, then the next page over. So our purpose, what are we doing today? The purpose of this 3-part lab is to observe and quantify or figure out with numbers the law of conservation of mass by gathering evidence and data and applying it to the law of conservation of mass in order to explain, prove, and support this concept. So our background information, again, from any of those videos, the law of conservation of mass, what is it? So we want to write down that it is the mass of a chemical reaction stays constant. And this is where the mass of reactants, or that starting stuff, equals the mass of the products. So part 1, like I said, we're going to do this one together. So part 1, background information. In this video, you'll observe a reaction between iron and oxygen. The chemical equation for the chemical reaction is this: 4Fe, so this is iron, plus 3O2, oxygen, combines together to form 2Fe2O3. So all these little numbers you'll figure out in chemistry, but it basically means how much there is of something. What we're going to do is identify the reactants of this chemical reaction above by underlining them. So it's always the starting stuff. So our reactants, or what we're starting with, is the iron and the oxygen. And then we're going to identify the products of a chemical reaction by circling them. So the products then would be over here on this side. Oops, sorry. So I'm going to grab that video quick. I'm not going to have it play because it's like 3 minutes, but I will show you what they are doing. All right, so this steel wool over here on the bottom is the iron, and we're going to take that and we are going to put it into an Erlenmeyer flask, and we're going to see how much it weighs before the reaction occurs and after the reaction occurs. So there's a closer up of a steel wool. It's just iron. You might have used it in like metal class to kind of buff out metal and make it shinier or make it less shiny. And then that's the Erlenmeyer flask we're going to put it in. And right now it's being kept with vinegar so that there's not a reaction happening, so that it stays like fresh. Okay, so here, let me move this. All right, so in a second, they will put on there it is, there's the beginning of the reaction. So we want to write down this number, the 137.48. That is the mass of the reactants. So on page 31, again, we have 137.48 grams. And then we want to be paying attention up here to what the balloon is doing during the reaction. So like right now, what is happening to the balloon? Where is it going? Just be sure to pay attention to that, what's going on. So then we're going to let the reaction go a little bit longer. This is time lapsed, so it's going faster. That's why you see the mass on the scale or the balance going up and down. It's fluctuating because it's been sped up. So there is a little slight bit of difference between the time lapse because air is moving around in the room. But then here they waited some time, and this is the final mass of the products. And if you look, it's also 137.48 grams. So we'll write that down. 137.48 grams. Okay, so then what evidence or observations did you see that proves a chemical reaction occurs when iron and oxygen react? So we did see the balloon getting sucked into the flask. I told you guys to pay attention and make note of that. You saw it kind of going into the flask that contained the iron or steel wool. And if something is getting sucked in instead of being blown out, so if you blow up a balloon and you're blowing out your oxygen or your air, the balloon gets larger because it's filling up with air. Now, if you inhale or you suck something in, that is taking in the oxygen. So the oxygen is being used up in that reaction because the balloon got sucked into the bottle. So oxygen was used. And then our next question, number 2, how did the mass of the reactants compare to the mass of the products? So basically these two numbers. How do they compare? They're exactly the same. So they're the same. Number 3, does the experimental data, so our data that we gathered here, support the law of conservation of mass? Let's go back and make sure we remember what the law of conservation of mass is. Law of conservation of mass is when the mass of the reaction stays constant. Therefore, the mass of the reactant, the starting stuff, equals mass of the products or the ending stuff. So is that true, first of all? Yes, that's true. We saw it here and we just said they are the same. So yes, it's true. And why? It's because the mass of the reaction did stay the same. The mass of the reactants equaled the mass of the products. So they are equal the same. So yes, it proves it. All right, so whether you're watching this video in class or you are at home, we are going to move on to the labs and the activities. You're going to need to do this background information before you can start. So before you can begin the lab, you need to show, if you're in person, you need to show me this background information that I'm about to give you. And if you are at home, you need to do the background information before you watch the videos. So once you have this down, we are going on to page 36. So it looks like this. It has Law of Conservation of Mass Lab right on top. It's page 36 if you numbered your book. All right, so one more time today. By the end of the day, you guys should be pros on what the law of conservation of mass is. It is the mass of a chemical reaction staying constant. And remember, the mass of the reactants, the starting stuff, is equal to the mass of the products. So we're going to use a few different things today for our lab. We're going to use vinegar, which is an acid. And we're going to mix it with baking soda, which is a base. So we're going to observe an acid-base reaction. So when we combine vinegar and baking soda in an acid-base reaction, it does cause a reaction, obviously. That produces or gives off a gas. Also, we might, we're going to figure out if we have our glow sticks or if anyone went and bought them, but we might have glow sticks. So if we do, or if you've ever played with one, or if you just know about them, basically when you have it uncracked, before it glows, there's two chemicals and they're separated by a little plastic tube on the middle. And then when you crack the plastic tube or like that glass tube, that's when they light up because the two chemicals that are in glow stick combine together and the reaction produces a light. So it's two chemicals that mix together to produce light, which shows that there's a reaction. So if you are in class in person, once you get that done, you can come up and show me or raise your hand, and then we can get started on the lab. So the directions will be given to you. They're on a purple sheet of paper if you're in class. If you are at home or if you're doing this as makeup, you just need to watch the videos. But you do have some questions. So you're first making a hypothesis of each one. So part one, you can make this hypothesis with me right now if you'd like. You're going to circle the choices in parentheses. So after I crack a glow stick, I think the mass of the glow stick plus the mass of the container, which is just the glow stick. So I'm actually just going to get rid of that. I think the mass of the glow stick, oops, want to keep that the same, will be, and then you pick, is it going to be the same or different than the beginning mass of the uncracked glow stick? So do you think it's going to be the same or different? You just circle one. And then, like I said, the procedure is either the video for you to watch or it is going to be given to you. And then don't forget, you do have data to collect. So you need to tell me the mass of the reactants plus the mass of the container before, and then once you crack it, after, and then observations, what happened, what occurred, if anything. And then you have a question. Did the results prove the law of conservation of mass? Yes or no? And how did you do this? If you don't remember, look back at the one we did together. Then you're going to have the vinegar and baking soda lab. So the procedure for this lab is also at your lab station, or it's given to you. So you have mass of reactants plus the mass of the container. So this time you're going to need to add the container onto your balance. And then you have the mass of the products once you combine them plus the mass of the container. And then you have these questions. So was the mass of the reactants plus the container the same or different? And then there's another page. So it says, does the data you collected support? Why or why not? And then think of something that you could have done to improve this experiment if something did not go well, or if your masses weren't the same, or if something happened. And then when you're done, you do need to watch the improved vinegar and baking soda experiment, whether you are in person or at home. This is a video, like it says here, demonstrated. So you're gonna take note of the video, again, write down the before, the after, and what happened. Then you do have your analysis questions. And right here for our CER, it is the claim, evidence, reasoning, conclusion. And your question, let me just grab that really quick. Our question that you're going to answer. Oops, did. All right, so did these labs follow the law of conservation of mass? So remember your claim, you answer this question. It should be a one sentence answer to the question, yes or no, they did or did not follow the law of conservation of mass. Evidence, you can bullet point the 3 that we did, or even the 4 that we did, saying how they did or did not follow. And then the reasoning, remember 4 sentences. We're going to take a look at the rubric that we gave you. So we gave you guys this rubric for a reason. It's not just to look pretty and fill up space. We do want you to use it. So need help with your reasoning? Step 1, restate your claim. Step 2, provide some scientific principles, knowledge that you already have about a topic. So probably, what is the definition of the law of conservation of mass? Step 3, provide data from the activity. So again, data means numbers. And then show how that connects. So proves or disproves this idea. And then step 4, you just wrap up or conclude. So that is your goal for the day.